Hi students, welcome to Physics for Everyone classes. This is your Satish sir. If you are watching this channel for the first time, please subscribe. In this video, I am dealing Faraday's laws of electromagnetic induction. There we have two laws. Faraday's first law, which is the qualitative analysis. The second is the Faraday's second law, that is quantitative analysis, which means to measure few parameters like induced EMF, induced current, all these things will come. Now, let us have a look at the Faraday's first law. The outcome of the law comes from the Faraday's experiments. We have over here a simple circuit. Let us see. There we are taking a circular coil connected to the galvanometer. The plane of the coil perpendicular to the plane of the board in this manner. You can imagine this palm is being like a circular coil. It is placed perpendicular to the board. So on the geometrical axis, let us consider a bar magnet. Here we can take the bar magnet. As you know, the bar magnet has got two polarities. The one is named as North Pole and second is the South Pole. The magnetic lines of force will start from North Pole and ends at the South Pole. There you can draw a few lines here, starting from North Pole like this and ends at the South Pole in this manner. As this magnet is kept beside the circular coil, these lines will pass through this coil, which means the flux is linked with the coil. But there is no deflection in the galvanometer. Later, he is moving this magnet towards the circular coil in this manner. As this magnet is coming closer to circular coil, the external magnetic flux passing through this coil gradually increases. And suddenly, he found some deflection in the galvanometer in one particular direction. Here, we are not discussing about the direction of the current which is induced in the coil. All these things will come under the Lenz's law. There we can discuss. After that, he is moving the same magnet away from the coil like this. And there we can expect the external flux passing through this coil gradually decreases, but still there is a sudden deflection in the galvanometer, but in the opposite direction. Through these observations, he made the one statement for the first law. You remember, throughout the lesson, the statement for the first law is been like this. Whenever the flux linked with the coil is been changing, either it increases or decreases, an induced current which is developed in the coil. If the flux which is passing through the coil is constant, there is no induced current developed in the coil. So that's about the first law of Michael Faraday. Next we can see Faraday's second law. We have just studied whenever there is a change in flux linked with the coil, there will be a induced current or induced EMF in the coil. So the second statement is that the induced EMF is directly proportional to the negative rate of change of magnetic flux linked with the coil. We can write in mathematical form E induced EMF which is proportional to minus d phi by dt. So where E is the magnitude of induced EMF, d phi by dt is the the rate of change of magnetic flux. Either it can increase or decrease. The negative sign plays a very important role. That only decides the direction of induced EMF and the direction of the induced current that comes under the Lenz's law. Now, if you expand this one, you can write E is equal to minus K into d phi by dt, where K is the proportionality constant. That we can take it as equal to 1 in SI system. So I am writing here induced EMF in SI system like this: E is equal to minus d phi by dt. The side we can write the value of K is equal to 1 in SI system. Now, inner flux can be expressed in more general form, like phi is equal to BA cos theta. So it comes as E is equal to minus d by dt of phi, we can write it as BA cos theta. So this is the induced EMF for a single turn. If you take more than one turn or n number of turns, the expression comes as the total induced EMF ET is equal to minus d by dt of n into BA cos theta, where n represents the total number of turns linked with the coil. So if you look at the expression, E is equal to minus d by dt of NBA cos theta. So what we can understand here, either of the four terms, if you change any one term, there will be the production of induced EMF in the coil, which means by changing the number of turns in the coil, EMF is induced, or by changing the magnetic field intensity passing through the coil increases or decreases, there we can expect induced EMF in the coil. Or else, if you change the area of cross section, the magnetic field linked with the area, if it is changing, there also induced EMF is developed in the coil. Or else, if we change the orientation of the coil in the given magnetic field, there also we can get an induced EMF in the coil. So out of four parameters, if we change any one parameter for the production of the induced EMF or induced current for the given coil,